Recall that we defined a vector space by giving it the minimum structure that will enable us to define linear functions. Therefore, in some sense, we already discussed the definition of a linear map. However, after studying vector spaces in much more detail, let us now return to the definition of a linear function or a linear map. A linear map L from V to W is a function that satisfies two conditions. It preserves vector addition and scalar multiplication. In other words, L of u plus v is equal to L of u plus L of v, and L of alpha times v is equal to alpha times L of v. Let us now look at some examples, starting with some of the examples we had seen before. One of the first examples of linear functions that we saw was the function f from R2 to R2 that takes the element x comma y in R2 to the element x plus y comma y minus x. More generally, we had discussed that any function from R2 to R2 that takes x comma y to ax plus by comma cx plus dy is a linear function. Let us verify once more that this function satisfies the two conditions that are required to be satisfied by a linear function. To prove this function is linear, let us first take two vectors in R2. Say u is equal to x1, y1 and v is equal to x2, y2. Then notice that f of u is equal to ax1 plus by1 comma cx1 plus dy1, and f of v is equal to ax2 plus by2 comma cx2 plus dy2. Therefore, f of u plus f of v is equal to ax1 plus by1 plus ax2 plus by2 comma cx1 plus dy1 plus cx2 plus dy2. But then we can rearrange this in the following manner. A into x1 plus x2 plus b into y1 plus y2 comma c into x1 plus x2 plus d into y1 plus y2. Now notice that this is equal to f of x1 plus x2 comma y1 plus y2. But x1 plus x2 comma y1 plus y2 is equal to x1 comma y1 plus x2 comma y2. And recall that x1 comma y1 is equal to u and x2 comma y2 is equal to v. Therefore, we see that f of u plus f of v is equal to f of u plus v. Further, notice that these two vectors u and v were completely arbitrary, and thus the first property is satisfied. Now let us try to prove that this function preserves scalar multiplication. So let v be an arbitrary element in R2 and alpha be a real number. Then notice that f of alpha times v is equal to f of alpha times x comma y, which is equal to f of alpha x comma alpha y, which is equal to a into alpha x plus b into alpha y comma c into alpha x plus d into alpha y, which can be rewritten as alpha times ax plus by comma cx plus dy, because alpha is there in all the terms, so we can take the alpha outside. But notice that ax plus by comma cx plus dy is equal to f of x comma y, and x comma y is the vector v. So f of x comma y can be rewritten as f of v. And thus we have completed the proof that f of alpha v is equal to alpha times f of v. Thus we have proved that the function that we were interested in satisfies both the conditions for being a linear function. In general, it is easy to construct linear maps from Rm to Rn. For instance, it is easy to construct a linear map from R2 to R4. One example would be xy getting mapped to 2x, 3y, x plus y and x minus y. It's easy to check that this is a linear map, and I leave the verification as a homework. But the trick is, if all the component functions are homogeneous degree 1 polynomials, then the function will be linear. This is something we have seen already. We are just going through these ideas once more. That's all. Now notice that similarly we can construct a linear function from, say, R3 to R2. I am emphasizing this different example because now the dimension of the codomain is lesser than the dimension of the domain. We are looking at this different example to stress that we can find a linear map from Rm to Rn irrespective of whether m is greater than n or m is less than n. One example of such a function would be the function x comma y comma z getting mapped to x plus y comma z. Once again, I will leave the verification as a homework, and the general principle is that the component functions should be homogeneous degree 1 polynomials. Let us now look at more interesting and natural examples. Let P be the set of all polynomials with real coefficients, and we will define a linear map from P to P. And this map I am going to call D. How is this map D defined? I take a polynomial P and I send it to the derivative of P. In other words, I send it to dP by dx. Now you might have learned that the derivative of the sum of two functions is equal to the sum of the derivative of the two functions. In other words, dp1 plus p2 by dx is equal to dp1 by dx plus dp2 by dx. Similarly, the derivative of alpha times p is also equal to alpha times derivative of p. So in other words, we have seen that this function is a linear function. We obtain another example of a linear map from P to P using integration. More precisely, we take a polynomial P and we send it to the indefinite integral of P. This again is a linear function, and it follows from properties of integral that you have learned in calculus. We know that integral of P1 plus P2 is equal to integral P1 plus integral P2. Similarly, integral alpha times P is equal to alpha times integral P. Both these two properties together mean that I is a linear map from P to P. Recall that we had seen that P, the set of all polynomials, is not a finite dimensional vector space. We had also mentioned that in linear algebra, we will primarily be interested in finite dimensional vector spaces. So we will restrict our earlier examples to a finite dimensional subspace of P, namely Pn, the set of all polynomials of degree less than or equal to n. Now notice that if you take the derivative of a polynomial of degree less than or equal to n, you will get a polynomial of degree less than or equal to n minus 1. Therefore, we can view D as a linear map from Pn to Pn minus 1. And this map takes P to its derivative. And as before, we can check that this function is a linear map. Similarly, we can restrict I to Pn. But notice that when you integrate, the degree increases by 1. Therefore, the function I will be from Pn to Pn plus 1. And as before, the function takes a polynomial to its indefinite integral. This is again a linear function. Having seen enough examples of linear maps, now I hope you have a reasonable understanding of linear maps. Let us now dig a bit deeper. This deeper understanding will also explain why it makes sense to restrict our attention to finite dimensional vector spaces. Let V be a finite dimensional vector space and let L from V to W be a linear map. Then notice that as V is a finite dimensional vector space, we can find a list V1, V2, etc. up to Vn, which is a basis for V. We can find such a list. Now notice that as V1 to Vn forms a basis for V, any element V in the vector space V can be written as V is equal to a1 v1 plus a2 v2 plus etc. up to an vn. Therefore, L of V is equal to L of a1 v1 plus etc. up to an vn. Now notice that in the definition of linearity, we just want the image of the sum of two vectors to be the sum of their images. However, this is true in general. The image of sum of n vectors is equal to sum of their images. And this proof is a simple application of mathematical induction. Therefore, I leave that as a homework. And thus, by this more general result, we get that L of a1 v1 plus etc. up to an vn is equal to L of a1 v1 plus etc. up to L of an vn. Once again, by linearity, we can rewrite L of a1 v1 as a1 times L of v1 and L of a2 v2 as a2 times L of v2 and so on. L of an vn is an times L of vn. Therefore, the moment we know the images of v1, v2, etc. up to vn, we can find the image of v. And this is true for any basis of v. Let us repeat, given any basis of the vector space V, the linear map L is completely determined by the image of all the elements in the basis. And this is what I had in mind when I said that the function is captured by finite data. The entire function is captured by the image of finitely many vectors. And that is very interesting. And for this, we wanted our vector space to be finite dimensional. And this is why we are restricting our attention to finite dimensional vector spaces. Hope that is clear to you. Let me end this video by explicitly stating the homework that I was mentioning in the previous discussion. Let V and W be two vector spaces. Notice that I am not assuming that the vector spaces are finite dimensional. They are arbitrary vector spaces. And let L from V to W be a linear map. Under this condition, if V1 to Vn are vectors in V, then prove that L of V1 plus V2 plus V3 plus etc. up to Vn is equal to L of V1 plus L of V2 plus etc. up to L of Vn.